A 2-ton block of stone rests in a desert, miles from any mountain. How did it get there? This is the core mystery of ancient engineering, the puzzle of moving enormous stones across impossible terrain. By the end of this journey, you will understand the toolkit of forgotten methods that let our ancestors literally move mountains. We will see how statues might have walked across islands and how stones could float across deserts. The stakes are nothing less than redefining human ingenuity. What do you believe was the true engine behind these impossible tasks? The challenge begins with a simple but staggering question. How do you move something that weighs as much as 500 cars? This is not about rolling a boulder down a gentle hill. The term impossible terrain is our starting point, and it means exactly what it sounds like. These are landscapes that actively work against you. Think of the dense, root-tangled jungles of Central America, where the Maya moved limestone blocks for their towering pyramids. Envision the steep, unstable slopes of a Peruvian mountainside, where Inca builders fitted multi-ton stones together without mortar. Picture the soft, shifting sands of the Egyptian desert, offering no solid footing for a colossal obelisk. Each environment presented a unique and brutal form of resistance. The ground itself was the first and greatest obstacle. Take the famous trilithon at Baalbek in Lebanon. 3 limestone blocks, each estimated to weigh over 800 tons, sit perfectly fitted on a raised platform. The quarry where they were cut lies nearly a mile away. The sledge and roller system. Think of it not as crude technology, but as applied physics on a monumental scale. The core components were straightforward: a sturdy wooden sled, a team of strong ropes, and a supply of smooth, rounded logs. The process was a study in coordinated motion. Workers would position the colossal stone block atop a heavy wooden sledge, lashing it securely. Teams would then take positions along long ropes, their combined strength directed by the rhythmic calls of overseers. As they pulled, other workers would constantly manage the log rollers. Just as the sledge passed over a roller at the back, that log would be sprinted to the front and placed back into the path, creating a continuous, renewable track. This transformed a sliding drag into a rolling motion, drastically reducing the force needed. Ancient Egyptian art provides a clear window into this practice. Tomb paintings from the Middle Kingdom vividly show a large statue being transported on a sledge, pulled by lines of workers, with a figure standing at the front pouring a liquid onto the ground. For a long time, this was seen as a ceremonial act, but modern physics experiments have revealed its brilliant practicality. Pouring water, or a slick mixture of water and clay, in front of the wooden runners dramatically reduced the coefficient of friction. It turned the sand from a grinding, resistant surface into a near-frictionless path. Researchers have calculated that with this lubrication, a team of just 10 people could pull a 1-ton stone. Scale that workforce up to the hundreds as the pharaohs could command, and moving the 2.5-ton blocks of the Great Pyramid's core becomes a matter of immense but achievable logistics. This method was perfectly suited to the flat, compacted sands of the Giza plateau. It was a triumph of leverage, not of muscle alone, using the earth itself as a tool. Yet, while this system explains movement across level ground, it immediately raises a deeper question. What happened when the path was not flat? What did the builders do when they faced a steep incline, or needed to navigate a sharp turn, or cross ground too soft even for lubricated sledges? The sledge and roller was a brilliant first chapter, but the story of ancient engineering was only just beginning to unfold. But a sledge can only go where the ground is flat. The true test of genius came when the stone needed to go up. Elevating a multi-ton block, whether onto a pyramid's rising tier or into the socket of a standing stone circle, required a different kind of magic. This was the domain of leverage and counterweight, a silent conversation between mass and balance. Here, ancient builders demonstrated a profound, intuitive grasp of physics, using simple materials to achieve controlled, impossible lifts. The most direct application was the lever. Imagine a long, sturdy timber, perhaps an entire tree trunk, placed under the edge of a massive stone. A smaller rock acts as the fulcrum, the pivot point. By applying downward pressure on the far end of the timber, a small team could lift the stone's leading edge just a few inches. Before it could settle back, workers would quickly slide wooden blocks or stone chocks underneath to hold that new height. Then reset the lever, lift again, and insert another block. Through this painstaking, rhythmic process of lift, support, and reset, a colossal block could be walked up a ramp or incrementally raised onto a platform. It was a method of immense patience, turning an impossible single lift into thousands of tiny, manageable ones. But for truly elegant vertical movement, the counterweight system stands as a masterpiece of early engineering. Picture a large A-frame structure built over the construction site. From its apex hangs a rope, and on one end of that rope is the stone to be lifted. On the other end is not a team of people, but a large container like a basket or a box. Initially, the stone is heavier, so it rests on the ground. Now, workers begin pouring sand into the empty container on the opposite side. Grain by grain, the container grows heavier. As its weight slowly approaches and then equals the weight of the stone, the system finds a delicate balance. With just a little more sand, the container becomes fractionally heavier, and with a gentle, controlled motion, it begins to descend, pulling the stone upward. The beauty of this system is its inherent safety and precision. The sand acts as a perfect brake. If the lift needs to pause, you simply stop pouring. There is no risk of a rope slipping or a team losing their grip. The weight of the earth itself is doing the work. This principle, a direct precursor to the modern crane, reveals an understanding of mechanical advantage that was both sophisticated and beautifully simple. It was not about overpowering the stone, but about outthinking its mass, about convincing gravity itself to become the primary laborer. From the fitting of lintels atop Stonehenge to the placement of the final capstones on Mesoamerican temples, this quiet ingenuity left its mark on the skyline of history. Yet, even this brilliant solution has its limits. It works superbly for lifting, but what about traversing vast, open distances where there are no frames or ramps? What do you do when your path is not a slope to climb, but a treacherous expanse of swamp, water, or loose, unstable soil? The next leap in ancient logistics required builders to change their perspective entirely, to stop fighting the terrain and instead ask it for a ride. Sometimes the most direct route is not a road but a river. This leads us to one of the most elegant and debated solutions in the ancient world, the idea of moving mountains by making them float. The waterway hypothesis suggests that when faced with an impossible overland journey, the builder's greatest innovation was to bring the water to the stone. Across multiple cultures, we see a tantalizing pattern: colossal construction sites positioned tantalizingly close to rivers, lakes, or coastlines. This proximity is unlikely to be a coincidence. It points to a logistical masterstroke, transforming back-breaking haulage into a buoyant, streamlined voyage. Consider the Great Pyramid of Giza. The quarries for its core limestone blocks were on the Giza Plateau itself, but the fine white Chura limestone for its gleaming outer casing, and the enormous granite blocks for its inner chambers, came from quarries hundreds of miles to the south. The idea of dragging these 70-ton granite beams all that way across the desert seems almost absurd, but a growing body of research, including the discovery of ancient harbor basins and water channels at the foot of the Giza Plateau, supports a compelling alternative. Egyptologists now propose that a sophisticated network of canals, fed by the annual flooding of the Nile, was engineered to bring barges laden with stone right to the construction site's doorstep. During the inundation, the desert's edge became a temporary marsh, and builders could have dug or deepened channels to create navigable waterways. A stone that would take thousands of laborers to drag could be floated on a simple, robust barge powered by a few oarsmen and the current itself. This was not just transport, it was hydraulic engineering on a grand scale, a seasonal reshaping of the landscape to serve a singular purpose. This principle finds a powerful echo far from Egypt, on the windswept Salisbury Plain of England. The smaller bluestones of Stonehenge, each weighing up to 4 tons, have a geological fingerprint tracing them to the Preseli Hills in Wales, over 150 miles away. The overland route is daunting, crossing rugged mountains and dense forests, yet a journey combining water and land, known as portage, paints a more plausible picture. Researchers suggest the stones could have been hauled down to the Welsh coast, loaded onto rafts or boats, and sailed along the coastline and up rivers that penetrated deep into the British interior. At the farthest navigable point, they would be unloaded and dragged the final, shorter distance overland. This mixed-method approach turns an epic trek into a series of manageable stages, each leveraging the easiest available medium. It reveals a mindset of profound adaptability. The true scale of ambition becomes clear when we realize that this method often required creating the waterway itself. Digging a canal, even a temporary one, to move a single colossal obelisk or a series of stone blocks, was a monumental act of preemptive labor. It meant that before a single stone could be moved, armies of workers had to first move unimaginable amounts of earth. This reframes our understanding of these projects entirely. The ancient planners were not just master builders, they were master landscape architects. They did not merely conquer the terrain, they negotiated with it, and when necessary, they redesigned it. They understood that sometimes to move a mountain, you must first bring the sea to meet it. Yet the waterway hypothesis, for all its elegance, could not solve every problem. On a remote, windswept island in the vast Pacific, the builders faced a challenge that canals could not answer. Here, the stones were not inert blocks, but towering, human-like figures with a center of gravity that seemed to defy movement altogether. The Moai of Easter Island stand as silent, monolithic giants, some weighing over 80 tons, carved from the hard volcanic rock of the Rano-Raraku quarry. The mystery is not just their creation, but their journey. How did these colossal statues travel miles across the island's rugged, hilly terrain to their coastal platforms? The answer may lie in a method so dynamic it feels almost alive, a technique that made the stones themselves appear to walk. Local oral tradition, passed down through generations, speaks of the Moai moving with a mana, a spiritual power guided by chiefs or priests. For a long time, this was interpreted as pure myth, but experimental archaeology has revealed a startlingly practical truth behind the legend. Researchers, working with a concrete replica of a Moai, demonstrated a technique that aligns perfectly with the stories. Teams positioned on either side of the statue would attach long, strong ropes to its upper portion. By pulling in a careful, alternating rhythm, one side and then the other, they could rock the statue from side to side. With each rocking motion, the statue's base would pivot slightly forward. This created a slow, swaying forward progression, a literal walking motion. Think of the careful, coordinated effort to tilt a heavy refrigerator or a grand piano from one corner to the next to navigate it through a hallway, but on a scale that defies belief. This walking method was not just clever, it was uniquely suited to the island's topography. Unlike dragging a sledge, which requires a cleared, level path, a walking statue could navigate the island's natural rises and dips. The rocking motion allowed the teams to control the descent of a slope with tension on the ropes, and to inch the figure uphill with sustained, rhythmic effort. It was a solution born from an intimate, intuitive understanding of physics, of center of gravity and momentum. The statue's own weight and shape became part of the mechanism. Each successful tilt was a tiny victory of balance over mass, repeated thousands of times across the landscape. This revelation does more than solve a logistical puzzle. It transforms our understanding of the event. The transport of the moai was likely not a silent, grueling haul. It was a coordinated, rhythmic communal activity. The pulling of the ropes, the shouted cues, the collective heave and pause would have created a powerful, almost ceremonial cadence. The line between practical engineering and spiritual ritual begins to blur. The journey of the stone from the mountain of its birth to its eternal watchpost by the sea was not just a means to an end. It may have been a profound, living procession, a way for the community to imbue the statue with life and purpose with every step it took. The stone did not just arrive at its destination, it walked there, animated by the will and the muscle of the people. This idea that the transport itself held deep meaning opens a door to a final, overarching question. If the journey mattered so much, what was the ultimate fuel that powered these impossible tasks? What force could organize thousands, coordinate years of labor and push human ingenuity to its absolute limits? The answer may be the most powerful and the most human tool of all. Yet for every elegant solution, there remains a whisper of doubt. What if the simplest answer is not about moving the stone at all, but about never needing to move it in the first place? This is the provocative heart of the geopolymer theory, a controversial idea that challenges the very foundation of how we see ancient construction. It proposes a radical alternative, that some of the most iconic stone blocks in the world were not quarried and hauled, but were instead cast like concrete directly where they stand. The theory focuses primarily on the limestone cores of structures like the Great Pyramid. Proponents point to curious details that don't quite fit the traditional carved stone narrative. They note the uncanny uniformity of some blocks, the lack of obvious tool marks, and the way certain stones seem to have flowed around embedded materials like fossil shells, rather than having those shells cut through. The suggestion is that ancient builders might have mastered a form of chemistry, creating an artificial stone. The process would have involved taking soft, naturally occurring limestone, crushing it, and then mixing it with a reactive binder, perhaps a type of natron or lime-based alkali, along with water. This would create a thick slurry, a kind of ancient geopolymer concrete that could be poured into simple wooden molds right on the building site. Once set, this material would harden into a block chemically identical to natural limestone. It is a compelling thought experiment. Suddenly, the logistics nightmare of moving 2.5 million multi-ton blocks evaporates. Instead of an army hauling stones, you have an industry producing them, turning local materials into perfect building units on demand. The transport problem transforms into a mixing and pouring problem, a challenge of chemistry and volume rather than brute force physics. This idea is not without its passionate critics, and it remains far outside the consensus of mainstream Egyptology. Experts point to clear evidence of quarrying at known sites, the discovery of stone-moving technologies in art and text, and the distinct geological signatures that match specific, distant quarries for certain stones like granite. The debate is intense, often hinging on the interpretation of microscopic details in the stone itself. But whether one accepts the theory or not, its greatest value may lie in the questions it forces us to ask. It pushes us to re-examine long-held assumptions with fresh eyes. We are so conditioned to think of ancient building as a subtractive process, of cutting away what is not the statue, of freeing the block from the mountain. The geopolymer theory asks us to consider an additive process, one of creation and assembly. It reframes the ancient builder not just as a master sculptor or logistician, but as a potential materials scientist, someone who understood the very essence of stone and how to reconstitute it. This shifts the pinnacle of their achievement from monumental effort to profound knowledge. The true innovation would not be in moving a mountain, but in knowing how to grow one, block by manufactured block, from the earth itself. It is a reminder that our understanding of the past is never complete, that a single new perspective can unsettle everything we thought we knew. And if the stones themselves might not be what they seem, then what other fundamental truths about these ancient projects are we still missing? The answer may lie not in the stone, nor in the journey, but in the invisible force that orchestrated it all, the human mind operating at a scale we are only beginning to comprehend. The partnership between human ingenuity and animal strength forms another critical chapter in this story. While we have marveled at the cleverness of sledges, levers, and waterways, we must also acknowledge a more direct source of raw power, the domesticated beast. The simple truth is that human muscle, even multiplied by the thousands, has its limits. To move the truly monumental, our ancestors learned to recruit partners from the animal kingdom, forging alliances that expanded the very scale of what was possible. The most universal of these partners was the ox. A team of oxen yoked together could generate a steady, immense pulling force far beyond any human team. This transformed the sledge from a human-powered device into a hybrid machine. On a prepared road or a lubricated path, a long train of oxen could haul stones that would have required an unsustainable number of people. This method shines a clear light on the logistical evolution of these projects. In cultures where cattle were domesticated and plentiful, such as in later Mesopotamian or Roman empires, the use of oxen became a standard, almost industrial, approach to moving heavy materials for roads, aqueducts, and monuments. It represented a shift from pure manpower to managed animal power, a significant leap in efficiency. But in some parts of the world, the animal of choice was far more majestic and powerful. Historical accounts and temple reliefs from South and Southeast Asia describe the use of elephants in construction. These intelligent, immensely strong creatures were not just symbols of royalty, they were living cranes and heavy haulers. An elephant, guided by a skilled mahout, could use its trunk and tusks to carefully position large stones or pull massive ropes attached to sledges. The psychological impact alone is worth considering. The sight of these gentle giants moving mountains of stone would have been awe-inspiring, blending the boundaries between natural power and royal command. This integration of animal labor represents a profound philosophical shift. It was no longer just humans bending the environment to their will. It was humans forming a collaborative partnership with nature. They leveraged the innate strength of other species, directing it toward a shared, monumental goal. However, this method also presents us with an important historical filter. For the very earliest megalithic cultures, like the builders of Stonehenge's first phases or the pyramid makers of pre-dynastic Egypt, widespread evidence for the large-scale domestication of cattle or the use of draft animals is sparse. The absence of such evidence suggests that many of the first, most mysterious moves were accomplished by human hands and minds alone. Animal power likely became a dominant force in later eras, an evolution in the ancient engineer's toolkit. It shows a trajectory from the foundational, back-breaking ingenuity of purely human methods to the enhanced, leveraged power of human-animal collaboration. This progression itself tells a story, one of continuous adaptation and resourcefulness. Yet, even with oxen and elephants in the mix, a haunting question remains for those earliest sites. If they lacked these powerful partners, what was the true engine that coordinated such vast efforts? The answer may lie not in physics or zoology, but in something far more intangible, the invisible architecture of the human spirit. The story of ancient builders finds a strange and compelling echo in the modern era. in the humid Florida night air of the early 20th century. There, a solitary man named Edward Leedskalnin, slight in stature and speaking with a thick Latvian accent, achieved something that should have been impossible. Working entirely alone, he single-handedly quarried, moved, and precisely carved over 1,000 tons of massive coral rock. The result is Coral Castle, a complex of monoliths, walls, and intricate sculptures including a 9-ton revolving gate so perfectly balanced a child could push it open. Leedskalnin was famously secretive, laboring only under cover of darkness and shooing away curious onlookers. He claimed to have rediscovered the building secrets of the ancient Egyptians, the very methods used to construct the pyramids. While investigators later found simple tools on his property, like homemade block and tackle rigs and tripods for leverage, the core mystery remains undiminished. How could one man, without modern machinery, manipulate stones weighing many tons each? His story captivates not because he used magic, but because he demonstrated that profound results can spring from simple, misunderstood principles. It is a powerful parallel to the ancient puzzles. Just as we look at Baalbek or Easter Island and assume it required thousands, we looked at Leedskalnin and assumed it required a crew. In both cases, we underestimated the potential of applied knowledge. He serves as a living reminder that techniques can be lost or simply overlooked, and that astonishing physical achievements can arise from a single determined mind working with the fundamental laws of physics. His castle stands as a monument to the idea that the spirit of ancient ingenuity never truly died. It simply went quiet, waiting to be rediscovered in a Florida field under the stars. But even the most robust sledge has a fundamental limitation. It needs a prepared path. What happens when the ground itself refuses to cooperate, when the final stretch to the sacred site is a labyrinth of boulders, roots, and sudden dips? For this, ancient ingenuity proposed a more nimble solution, a method that embraced the uneven ground rather than fighting it. This is the concept of the terrain-adapting cradle. Picture not a flat sled but a sturdy wooden frame, almost like a shallow, rectangular box built tightly around the stone. This cradle cradles its heavy passenger securely, but its true genius lies in its mobility. Instead of sliding, it is designed to rock and pivot. As the team encounters a protruding rock or a shallow trench, they don't stop to clear it. Instead, workers use stout wooden poles as levers, inserting them under one side of the cradle. With coordinated effort, they lift that side just enough to clear the obstacle. They then pivot the entire assembly forward or sideways before lowering it down. Then they move to the other side and repeat the process. It is a slow, deliberate dance, a series of tiny adjustments that turns an impassable slope into a navigable staircase. This method would have been painstakingly slow, an exercise in immense patience, but its value was in its supreme adaptability. It was the perfect tool for the last mile, for those final, critical yards where building a smooth road or canal was impossible or impractical. Imagine the final approach to a remote stone circle nestled in a natural hollow, or the ascent to a cliffside temple where the bedrock broke through the soil. Here, the cradle shines. It transforms the problem from one of landscaping, of moving earth, back into one of pure mechanics and leverage. The workers are not battling the terrain, they are conversing with it, negotiating each stone and depression individually. This idea exemplifies a deeper principle in ancient engineering, a principle of radical pragmatism. These builders were not applying a single, universal solution. They were master tacticians, assembling a toolkit of methods and selecting the right one for the specific challenge in front of them. The flat desert called for the lubricated sledge. The steep incline demanded the lever and counterweight. The long-distance journey begged for the waterway, and the final, rugged approach required the adaptable cradle. This reveals a mindset far removed from our modern reliance on standardized machinery. It was a fluid, responsive intelligence, one that saw the environment not as a blank slate to be dominated, but as a complex partner in the project, full of both obstacles and opportunities. The true monument was not just the final standing stone, but the accumulated wisdom of knowing how to get it there, a wisdom written not in books, but in the very paths worn into the earth. But all these ingenious methods share a single, indispensable source of power. The true machine behind these feats was not made of wood or rope, but of people. The most overlooked element in moving mountains is the staggering social engine required to make it happen. Transporting a megalith was an act of profound organization, a logistical ballet that required feeding, housing, and coordinating thousands of individuals, often for years on end. This was social engineering on a scale that rivals the physical engineering. Think about the practicalities beyond the pull of a rope. Where did all those workers sleep? What did they eat, and who prepared it? How were tools maintained and replaced? Who ensured the quarry teams, the transport crews, and the final placement specialists were all in the right place at the right time? The answers reveal a hidden infrastructure of support, a vast, moving city dedicated to a single purpose. This level of coordination points to something we often miss when we stare at silent stones: sophisticated administrative systems with clear hierarchies. There would have been overseers who planned the routes, engineers who understood the mechanics of leverage, and logisticians who managed supply lines of food, water, and materials. It was a civilization operating at peak capacity, marshalling its greatest resource, its collective human will. So what motivated such an immense, sustained effort? The fuel for this social engine likely came from multiple sources. For many agricultural societies, the off-seasons between planting and harvest presented a natural window for large communal projects. This was a time when labor could be directed toward monumental works without crippling the food supply. In other contexts, deep religious or spiritual belief provided a powerful unifying force. The act of building a temple or raising a sacred stone could be seen as a direct service to the gods, a communal prayer made physical, and of course, the concentrated power of a centralized state, a pharaoh or a king, could command labor as a form of tax or duty, channeling the entire population's energy toward a symbol of royal authority. Yet to see this only as top-down coercion misses a profound human truth. The movement of a stone this large was inherently a communal act. It required absolute trust and synchronization. Every pull on a rope had to be in unison. Every lift with a lever demanded perfect timing. This shared struggle, this collective triumph over an impossible task, would have forged incredibly strong social bonds. It transformed a diverse population into a single, purposeful organism. The finished monument, then, was more than a building. It was a permanent testament to what that society could achieve together. It proved that their shared identity was strong enough to literally reshape their world. The greatest structures in history were built not just with hands, but with shared purpose, meticulous planning, and the invisible, powerful architecture of human cooperation. This realization shifts our gaze from the stone itself to the society that moved it, and asks one final, lingering question. If they could organize so brilliantly for a single project, what other aspects of their world did they understand that we have yet to rediscover? The ingenuity of ancient builders could even harness the cold. In the northern reaches of Europe, where winters are long and deep, another elegant solution emerges from the landscape itself: ice. For cultures in these regions, the bitter season was not a time of halted work, but a unique logistical opportunity. Frozen ground, lakes, and rivers transformed into nature's perfect low-friction highways. The concept is brilliantly straightforward. A stone that would sink into soft summer earth or resist every pull on muddy soil becomes almost manageable when the world turns to ice. The evidence for this method is more theoretical than archaeological, as ice leaves no permanent trace, but its practicality is undeniable. Imagine a large stone block placed on a wooden sledge at the edge of a frozen lake. The slick, perfectly flat surface of the ice offers almost no resistance. Teams could pull loads across distances that would be exhausting or impossible in other seasons, turning a formidable water barrier into a smooth, solid road. But the true innovation likely went a step further. Builders could have actively engineered their own ice pathways. By channeling or spraying water along a desired overland route, they could create a custom ice slide, a glistening ribbon of frozen transport leading directly to the construction site. With each application of water, the track would become smoother and harder, a self-renewing surface that required minimal maintenance beyond the initial effort. The physics are compelling. The coefficient of friction on ice is exceptionally low, meaning the pulling force required could be a fraction of that needed on dirt or sand. What might demand 200 people in autumn could be accomplished by 50 in the heart of winter. This method represents a profound synchronization with the natural world. It was not about conquering the environment with relentless, year-round labor, but about observing its rhythms and inserting human ambition into the seasonal cycle. The builders were listening to the world, waiting for the moment when the land itself would offer up its secret, a temporary highway of crystal. This approach reframes our view of these monumental projects. They were not necessarily continuous, frantic races against time. They could have been patient, cyclical endeavors with different phases of work aligned with the turning of the year. Quarrying might occur in the dry summer, rough shaping in the autumn, and the grand movement of the heaviest stones reserved for the deep freeze of winter. It turns a liability, the harsh northern cold, into the project's greatest asset. While we may never find a definitive tool marked for ice transport, the elegance of the idea fits perfectly within the ancient engineer's mindset of radical adaptation. It shows a flexibility that is humbling. They did not have one single answer to the problem of moving mountains. They had a repertoire of answers, and they chose the one that sang in harmony with the land, the climate, and the time of year. The silent, frozen forests of the north may have once echoed with the sounds of progress, as stones glided effortlessly over a world temporarily made smooth by the cleverness of human foresight. This adaptive spirit leads us to consider the ultimate purpose behind such immense effort. Yet beyond the tangible world of sledges, levers, and ice lies a realm of pure speculation, where physics seems to bend toward myth. Among the most exotic theories ever proposed is the concept of acoustic levitation, the idea that sound itself could lift mountains. This hypothesis lies on the farthest fringe of historical interpretation, suggesting that ancient builders discovered specific resonant frequencies, perhaps through chanting, drumming, or the use of specialized instruments that could somehow negate gravity's pull. In this imagined scenario, a massive stone would become almost weightless, hovering above the earth, guided effortlessly into place by the directed will of sound. While there is not a single shred of scientific evidence that such technology existed in antiquity, the persistence of these legends across disparate cultures is itself a fascinating artifact. From vague allusions in certain esoteric texts to modern retellings of lost sonic science, the story endures. Its power lies not in its plausibility, but in what it reveals about us. It speaks to a profound, almost universal human longing to believe that our ancestors possessed a secret wisdom, so advanced it borders on the magical, a key that could unlock the universe's hidden forces and make the impossible simple. In a way, it is the ultimate expression of our awe. When faced with a stone block that logic says cannot move, part of us wishes for a solution that transcends brute force altogether, a command whispered to the universe that makes the stone obey. These stories, however fanciful, serve an important purpose in the larger narrative. They remind us that for the people who built these monuments, the process was likely not seen through our modern, purely technical lens. The line between advanced engineering and sacred ritual was often invisible, beautifully blurred. The rhythmic pull on a rope could be a prayer. The precise placement of a lever could be an act of devotion. The coordinated effort of thousands could be a living ceremony. In such a worldview, the use of sound, of resonant chanting to focus collective intention and synchronize movement, is not so far-fetched. It may not have levitated the stone, but it could very well have levitated the human spirit, aligning the hearts and muscles of the workers into a single, potent force. So while we must ground our understanding in the physical methods of sledges and counterweights, we should not dismiss these legends of sound. They are the echo of a deeper truth, that the greatest achievements of the ancient world were symphonies of both muscle and meaning, where every practical action was infused with a sense of the profound. This blending of the material and the spiritual may be the most sophisticated technology of all, one that we are still learning to fully appreciate. The ultimate challenge was not moving a stone across the earth, but lifting it into the sky. To raise a block to the top of a growing pyramid, 100 feet or more in the air, ancient engineers performed one of their greatest acts of transformation. They turned the sheer face of a cliff into a gentle slope. This is the power of the inclined plane, and in the ancient world, it took the form of monumental ramp networks. Think of these not as simple paths, but as temporary mountains built by human hands, colossal earthen structures that allowed builders to walk their stones right up to the heavens. The principle was beautifully simple, trading a brutal vertical lift for a long, manageable, gradual climb. By extending the distance over which the force was applied, the steep angle of effort softened. Pulling a heavy sledge up a long, gentle slope, while still immense work, was fundamentally possible in a way that hoisting the same weight straight up was not. The construction of these ramps was a project mirroring the monument itself. As each new course of stone was laid on the pyramid, armies of workers would haul basket after basket of rubble, earth, clay, and gypsum plaster to extend and heighten the ramp, maintaining that critical, gentle gradient all the way to the new working level. The ramp became a living, growing entity, a sprawling artificial landscape clinging to the side of the sacred geometry. But the design of these ramps was not one size fits all. Evidence and debate point to several ingenious variations. A single, straight ramp shooting directly at one face of the pyramid would have been simplest, but as the structure rose, this ramp would have to become impossibly long and require staggering volumes of material. So, engineers likely adapted. One compelling theory suggests the use of a zigzagging ramp that wrapped around the pyramid's faces, like a giant switchback road going up a mountainside. This design used the structure's own footprint for support, requiring less imported fill. An even more fascinating idea is that of an internal spiral ramp, built within the rising core of the pyramid itself. As the outer casing stones were placed from the top down, this internal corridor, lined with timber, could have provided a protected, direct route for delivering blocks to the highest levels, later being filled in as work concluded. The true scale of this endeavor comes into focus when we consider the final act, the dismantling. Once the capstone was set, the great ramps had served their purpose. Then came the equally colossal task of deconstruction, of moving millions of tons of ramp material away to reveal the perfect, smooth-sided pyramid beneath. This was not a messy aftermath, it was the final, deliberate unveiling. The ramp was the temporary scaffold for a permanent dream, a disposable mountain that gave birth to an eternal one. It demonstrates a breathtaking long-term vision where the means of construction were designed to vanish, leaving only the miracle behind. This method, more than any other, embodies the ancient builder's philosophical approach, a profound patience that measured progress not in days, but in generations, willing to move a universe of earth just to make a single stone's journey possible. A stone's journey relied on something surprisingly fragile, a rope. The grandest lever or the most perfectly engineered sledge was useless if the cord connecting human effort to stone mass snapped under the strain. This brings us to a hidden pillar of ancient engineering, the advanced materials science of everyday objects. The true test of a civilization's capability often lay not in its grand designs, but in the quiet strength of its simplest tools. Consider the humble rope for moving megaliths. This was not just cordage, it was a critical load-bearing component, a high-tension cable holding the entire enterprise together. Ancient rope makers were master craftsmen, working with materials like papyrus reeds, flax fibers woven into linen, hemp, or even braided leather. The process of creating a rope strong enough to pull 80 tons was an industry in itself. It involved harvesting the right plants at the perfect time, retting them to separate the long, strong fibers, then painstakingly twisting and braiding those fibers into ever thicker, ever stronger lines. The knowledge of how to twist fibers so they gripped each other, how to maintain consistent tension during weaving, and how to seal and protect the finished product from the elements. This was specialized, vital technology passed down through generations. A single weak point in a 100-yard hauling line could mean disaster, sending a multi-ton stone careening out of control and endangering hundreds of lives. The rope was the literal lifeline of the operation, but the connection between the rope and the ground was just as crucial. We've seen the tomb paintings of liquid being poured before a sledge, and modern physics has confirmed its stunning effect. Wetting the sand or clay path in front of the wooden runners could cut the required pulling force in half. But this likely wasn't just any water. Think of the context. These were projects of supreme importance where every advantage was sought. It is highly probable that builders experimented with and employed specialized lubricants to maximize this effect. They might have used water mixed with fine clay to create a slick, muddy slurry. They could have utilized animal fats or plant-based oils, substances they knew reduced friction in other applications. The choice of lubricant would have been a careful decision tailored to the local soil type. On the dry, sandy plateaus of Egypt, water alone would soak away quickly, so a thicker mixture might have been essential to maintain that critical slippery film. This turns a simple act into a sophisticated material application. It was early tribology, the science of friction, wear, and lubrication, practiced on a colossal scale. The synergy of these elements paints a complete picture. The strong rope transmitted the force, the effective lubricant minimized the resistance, the wooden sledge distributed the weight, and the coordinated human or animal power provided the drive. Each component was a refined technology in its own right. A failure in any one link, a rotten rope, an ineffective slurry, a cracked sledge runner, could bring the entire monumental effort to a halt. This changes our perspective entirely. We often marvel at the stone and wonder how it moved, but the true marvel may have been the ecosystem of innovation that surrounded it, an entire support network of crafts and chemistry that had to be perfected long before the first pull on the rope could even begin. The silent, forgotten strength of a braided fiber and the slickness of a prepared path were as foundational to these wonders as the genius of the architect. They remind us that history's greatest leaps were never made by a single brilliant idea, but by 1,000 small, perfected details working in flawless, invisible concert. The wind that sculpted desert dunes might have also helped to build pyramids. This is the heart of the Kite Hypothesis, a modern idea that proposes ancient builders harnessed the sky itself as a laborer. The concept was championed by engineer Maureen Clemens, who looked at the challenge of moving enormous stone blocks and saw a missed opportunity. She noted the powerful, consistent winds that sweep across the Egyptian landscape and asked a radical question. What if those winds were not just a force to endure, but a force to employ? Her theory suggests that large, carefully designed kites, made from materials like linen or papyrus, could have been attached to heavy sledges. On a windy day, the kite would catch the air and generate substantial lift or pulling force, effectively lightening the load for the teams on the ground, or even providing the primary motive power for movement. It is a vision of ancient construction that feels almost poetic, where the very air aids in raising monuments to the heavens. To test the idea, modern teams have conducted remarkable experiments. Using large, contemporary parafoil kites, researchers have successfully lifted multi-ton stone obelisks off the ground and pulled heavy concrete blocks across desert flats. The demonstrations are visually stunning and scientifically valid, proving that the physics of the concept are sound. A strong, steady wind acting on a large enough airfoil can indeed produce forces measured in tons. This practical verification forces us to take the hypothesis seriously, not as fantasy, but as a plausible application of aerodynamics that could have been discovered through observation and trial. Of course, the significant caveat is the lack of direct archaeological evidence. No ancient Egyptian tomb painting depicts a team flying a giant kite, and no kite rigging has been found in the archaeological record. This absence means the idea remains in the realm of fascinating speculation rather than accepted history. Yet, its true value may not lie in proving a specific historical fact. The kite hypothesis serves a deeper purpose. It fundamentally challenges our perspective on ancient innovation. It asks us to look at the environment through the eyes of a resourceful builder and see not just obstacles but hidden allies. The sun, the wind, the water, the ice, these were not just backdrops. They were a palette of invisible forces, each with the potential to be understood and directed. Whether or not Clement's specific vision is correct, it expands our imagination of what was possible. It reminds us that the toolkit of the ancient world included every element of nature, waiting for a clever mind to recognize its utility. The hypothesis underscores a recurring theme in this entire story, that the greatest engineering feats often came from seeing the world differently, from asking not what you lack, but what you already have in abundance. In a land of constant wind, ignoring that power would almost be stranger than using it. So while we may never know if kites truly flew over Giza, the idea itself lifts our understanding, showing that the boundaries of ancient ingenuity were as vast as the sky above them. The stark contrast between a desert plateau and a mountain peak reveals the true nature of ancient ingenuity. To see this in action, we can place two legendary sites side by side, the pyramids of Giza in Egypt and the mountaintop citadel of Machu Picchu in the Peruvian Andes. On the surface, they share a common goal, to build something monumental with stone, but the landscapes they occupy could not be more different, and so the methods they demanded became unique expressions of human creativity. In the flat, expansive deserts of Egypt, the environment offered certain gifts and certain challenges. The compacted sand provided a stable, if resistant, surface. The annual flooding of the Nile created a seasonal highway. Egyptian solutions, therefore, leaned into these conditions. They perfected the lubricated sledge to glide across the desert floor. They engineered vast networks of canals and harbors to float stone on barges. They constructed colossal earthen ramps, turning vertical climbs into long, gentle slopes. The Egyptian approach was one of horizontal movement and managed ascent, a dialogue with sand and river. Now transport your mind to the Andes. Here, the Inca builders faced a world of verticality. Machu Picchu was not placed on a convenient plain. It was deliberately set upon a narrow ridge between two soaring peaks, with steep cliffs plunging into river valleys below. There were no flat highways here, no navigable rivers at this altitude. The terrain itself was the ultimate obstacle course. Granite blocks, some weighing over 50 tons, were quarried from sites further down the mountain. Moving them up to the building site was an act of defiance against gravity itself. Their toolkit had to adapt. While they may have used sledges on rare, level stretches, the primary method was almost certainly a more direct, incremental form of lifting. Imagine a system of strong ropes, likely made from braided leather or plant fibers, anchored to sturdy posts or natural rock outcrops higher up the slope. Teams of workers would use these ropes, combined with wooden levers, to painstakingly walk each block upward. They would lift one edge, slide a stone or timber underneath for support, then move to the opposite side and repeat. It was a slow, swaying dance up the mountainside, a testament to immense patience and coordination. Earthen ramps were still used, but here they were not long, straight causeways. They were likely switchbacking paths carved into the cliffside, temporary scaffolds of soil and stone that followed the brutal contours of the land. This comparison dissolves the myth of a single lost secret. There was no universal ancient blueprint for moving megaliths. Instead, there was a deep, global understanding of fundamental principles, leverage, friction reduction, and the use of counterweights. These principles formed a shared intellectual toolkit. What varied spectacularly was the application. In Egypt, the principle of reducing friction meant pouring water on sand. In the Andes, it might have meant polishing the stone's base or using smooth, wet clay on timber rails. The principle of leverage in Egypt raised stones on a grand ramp, while in the Andes it inched them up a muddy footpath. The terrain dictated the technique. This is not a story of separate, isolated genius, but of a unified human genius responding to 1,000 different puzzles. The sand demanded one answer, the mountain demanded another, and in both places the builders listened. They proved that the most powerful tool was not a specific device, but the adaptable, observant, and relentlessly creative human mind. This adaptive spirit raises a final, humbling thought. If our ancestors could achieve so much by working in harmony with their world, what might we learn from their example today? The journey of Stonehenge's giant sarsen stones presents a unique puzzle. These towering monoliths, each weighing up to 30 tons, were brought from the Marlborough Downs over 20 miles away. The traditional image is of a long, cleared road, a highway of logs stretching across the entire distance. But archaeologist Mike Pitts proposed a different, more nimble solution, the lily pad theory. This idea reimagines the landscape not as a path to be conquered, but as a series of stepping stones to be utilized. Instead of constructing one continuous, perfectly level track, workers could have prepared a sequence of sturdy platforms made from timber or even smaller stones. These platforms would act like lily pads on a pond, discrete and stable points scattered across the challenging terrain of the Salisbury Plain. The process would have been a rhythmic cycle of leverage and balance. A sarsen stone would be carefully levered up and onto the first platform. Once secured, teams would then use poles and ropes to tip or rock the stone forward, guiding it to fall onto the next prepared platform a short distance away. It was a controlled, hopping motion, moving the colossal weight in a series of deliberate, manageable leaps. This method offered brilliant advantages for crossing the boggy, uneven ground. A long log road would sink into soft earth or require constant leveling. A lily pad, however, is a localized solution. You only need to stabilize the ground directly under the platform itself, not the entire 20-mile route. If one area was too wet, you could simply adjust the placement of the next pad, navigating around the obstacle. It turns an immense linear problem into a modular one, solving the journey point by point. This theory speaks to a deeper logistical intelligence. It shows ancient planners breaking down an impossible task into a sequence of identical, repeatable steps. The focus shifts from the daunting whole to the achievable unit, from moving a stone 20 miles to moving it just 20 feet, over and over again. It is a philosophy of incremental victory where patience and precision triumph over raw, continuous force. The lily pad method may not have been the only way, but it embodies a strategic mindset we see echoed in other ancient wonders. the wisdom to tackle a giant not with one great push, but with 1,000 perfectly placed nudges. A stone's true weight was measured not in tons but in meaning. While we analyze the physics of sledges and levers, we must also consider the invisible fuel that powered these engines of human effort, a profound and shared belief. For the societies that undertook these projects, the colossal stones were never inert material. They were living entities, vessels for the divine, permanent homes for ancestral spirits, or direct conduits to the cosmic forces that governed their world. The act of moving them, therefore, was far more than a construction job. It was a sacred procession, a collective ritual that physically enacted their most deeply held truths about the universe and their place within it. This spiritual dimension transforms our understanding of the labor. Enduring blistered hands, aching muscles, and years of toil under the sun takes on a different character when the work is seen as a direct service to the gods, a prayer made manifest through shared struggle. The hardship was not meaningless drudgery, it was a form of devotion, a necessary trial that purified the community and sanctified the stone with every inch it traveled. This belief system provided a unifying purpose so powerful it could coordinate generations. A worker might never see the finished pyramid capstone set in place, but he knew his effort was part of an eternal project that connected him to his ancestors and his descendants. His labor was a stitch in the fabric of cosmic order, helping to ensure the sun would rise, the Nile would flood, or the seasons would turn. The psychological impact of this cannot be overstated. It fostered an innovation born not just of necessity, but of sacred intent. Finding a better way to lubricate a sledge path wasn't just about efficiency. It was about honoring the deity within the stone by ensuring its journey was smooth and respectful. Designing a flawless counterweight system was an act of reverence, a way to lift the divine presence skyward with grace and precision. The process itself was transformative. By the time a monolith reached its final resting place, it had been imbued with the sweat, songs, and steadfast intention of an entire people. Its value was multiplied 1,000-fold by the journey. This reveals the ultimate and perhaps most sophisticated tool in the ancient builder's arsenal, the human mind and spirit, aligned by a common vision. The greatest monuments ever built stand not just as triumphs of engineering, but as testaments to what people can achieve when they are united by a story greater than themselves. The physics of friction holds a hidden secret, a counterintuitive trick that ancient builders might have mastered through sheer feel. This is the bounce technique, a method where steady, brutal pulling is abandoned for a rhythmic, almost playful motion. Modern experiments have revealed that overcoming static friction, the initial force that glues a resting object to a surface, often requires more energy than keeping it moving. The breakthrough comes from getting the stone to break its static bond not with a slow, constant strain, but with a sharp, coordinated jolt. Imagine teams not pulling in a continuous heave, but instead taking up the slack in their ropes and then, on a shouted command, giving one powerful, unified jerk. This sudden impulse can pop the sledge free from the grip of the sand or clay. Once it's moving, even slightly, the effort to keep it going drops dramatically. The process then becomes a cycle, a rhythmic dance of tension and release. Pull, bounce, slide, pull, bounce, slide. This transforms the work from a test of raw endurance into a test of perfect timing. It leverages the stone's own inertia against the sticking power of the ground. The equipment could be simple, a long, springy lever placed under the sledge's edge. Workers would press down in unison, using the timber's flex to literally bounce the entire load forward an inch or two before resetting. The gains in efficiency, while subtle on a single pull, would compound over the miles of a journey, potentially saving immense amounts of collective energy and reducing the strain on every individual. This insight shifts our view of the labor from a grim, silent haul to something more dynamic. It suggests a worksite alive with cadence and coordination, where overseers might have chanted or used drums to keep the rhythm, turning physics into a kind of music. The bounce technique reveals that the true innovation wasn't always in the tool, but in the movement itself, in an intuitive understanding that sometimes, to move a mountain, you must first learn how to make it dance. Theories on a page are one thing, but the real test comes when you try to move the stone yourself. This is the power of experimental archaeology, a field that trades speculation for sweat and data. It asks a beautifully simple question: what happens when we actually try to do it? Researchers around the world have become modern-day apprentices to the ancient builders, constructing replicas of sledges, fashioning ropes from traditional materials, and pouring their own ramps of earth and plaster. Their laboratories are not sterile rooms, but open fields and desert flats. In Egypt, the archaeologist Mark Lehner has led extensive experiments, hauling concrete blocks on wooden sledges to measure the precise forces involved. Across the ocean, teams from institutions like University College London have investigated the transport of Stonehenge's bluestones, testing whether they could have been moved on a cradle of wooden rollers or by boat. The process is methodical and revealing. They load a sledge, attach ropes, and pull. They use force gauges to record exactly how many pounds of tension are required to get the load moving and to keep it going. They note how different lubricants, water versus clay slurry, affect the friction. They study the wear patterns on the replica sled runners and the crushed state of the log rollers after just a few hundred feet of travel. This hands-on science transforms elegant hypotheses into hard, sometimes messy, numbers. It has delivered crucial validations. Experiments have conclusively shown that wetting the sand in front of a sledge can cut the required pulling force by half or more, turning a tomb painting detail into a proven engineering technique. They have demonstrated that a team of a few dozen people, using simple leverage and rocking motions, can indeed walk a multi-ton statue like the Moai. But this discipline is just as valuable for what it rules out. Some proposed methods, which seem clever in theory, prove wildly impractical or dangerously unstable when attempted at full scale. This trial and error process in the present day gives us a profound empathy for the past. We feel the burn in our muscles, the strain on the ropes, the frustration when a lever slips. We gain an intimate appreciation for the incremental nature of the work, for how a journey of miles truly is made of millions of individual pulls and adjustments. This field is our closest possible link to the ancient engineer's mindset. It proves that their knowledge was not mystical, but deeply empirical, forged in the physical world through observation, adaptation, and relentless practical problem solving. By getting our hands dirty, we don't just learn how they might have moved mountains, we begin to understand why their solutions were so brilliantly, inevitably, right. The final form of a stone is not always its traveling form. This leads us to a principle of profound logistical efficiency, the potential of prefabrication. The idea is brilliantly pragmatic. Why carry the entire, finished weight of a statue or an architrave if you don't have to? There is compelling evidence from sites around the world that many megaliths began their journeys not as polished masterpieces, but as rough, blocky masses, intentionally left incomplete. The final, delicate shaping was reserved for the destination. This was not a compromise, but a masterstroke of planning. Consider the iconic Moai of Easter Island. At the Rono-Raraku quarry, hundreds of statues remain in various stages of completion, many still partially attached to the bedrock. What's fascinating is that the vast majority of these quarry-bound figures are only roughly carved. Their distinctive facial features, their detailed hands, the fine lines on their backs, these were often added later. The primary goal at the quarry was to free a basic humanoid shape from the rock, a shape that was easier to transport because it retained a sturdy, rectangular base and lacked fragile protruding details that could snap off during the arduous journey across the island. The statue was essentially prefabricated in its heaviest, most robust form, with the artistic refinement saved for the ceremonial platform where it would finally stand. This same logic echoes in the stone circles of Europe and the pyramids of Egypt. At Stonehenge, the giant sarcens show clear signs of final dressing on site. The characteristic mushroom-shaped tenons on top of the uprights, designed to lock into the lintel stones above, were almost certainly carved after the monoliths were erected. Trying to transport a 30-ton stone with such precise, fragile protrusions already in place would have been an invitation for disaster. Similarly, the exquisite outer casing stones of the Great Pyramid, which once formed a smooth, gleaming white surface, were likely given their final, perfect fit and polish only after they were raised into position on the pyramid's sloping sides. This division of labor reveals a society operating with sophisticated, almost industrial foresight. It implies distinct specialist teams, the quarry workers who excelled at the brute force extraction, the transport crews who understood the physics of movement, and the master carvers and fitters who possessed the artistic and geometric skill for the final assembly. Each stage was a specialized phase in a grand production line. The logistical benefit is immense. Transporting a rough block instead of a finished sculpture can reduce its weight significantly by eliminating excess stone. More importantly, it dramatically lowers the risk of damaging the irreplaceable final product during the most hazardous part of the process, the journey itself. A chipped ear on a statue or a cracked decorative edge on a building block could be catastrophic if it happened miles from the site. But if that detail hasn't been carved yet, there is nothing to chip. This approach turns an impossibly fragile undertaking into a series of robust, manageable operations. It shows us that ancient planners thought like modern engineers, breaking down a monumental vision into sequential, fault-tolerant steps. The true masterpiece was not just the finished stone, but the invisible blueprint that guided it safely and efficiently from mountain to monument. Every monumental achievement leaves a mark upon the earth, a subtle signature written in the soil. The sheer scale of moving mountains of stone demanded mountains of other resources, and the environmental legacy of these projects is a story told in tree rings and compacted earth. For every sledge that glided across wet sand, trees were felled to build it. For every log roller placed beneath a colossal block, a forest provided the raw material. The demand for timber was immense and relentless, not just for transport but for the scaffolding, the levers, and the sprawling ramp networks that clung to the sides of rising pyramids. In regions where these projects spanned generations, the cumulative effect could lead to significant local deforestation, altering ecosystems and forcing builders to seek wood from ever greater distances. This resource pressure is a silent footnote in the grand narrative, a reminder that these wonders were built from a living, finite world. The earth itself was reshaped in more direct ways. The construction of a massive earthen ramp required the movement of hundreds of thousands of tons of soil, clay, and rubble. These temporary mountains, later dismantled, still left their imprint, compacting the ground beneath and changing drainage patterns across the landscape. Roads worn smooth by the passage of countless sledges and feet became permanent features, etching new lines into the terrain. Yet, these very scars are what allow archaeologists to piece together the methods. The compacted soil along a suspected transport route, the absence of certain tree pollens in sediment layers from the construction era, the distinct tool marks on quarry walls, these are the environmental clues that help map the ancient workflow. They reveal not just how a stone was moved, but the vast, hidden economy that supported its journey. This legacy is beautifully dual. We inherit the awe-inspiring monument, a testament to human vision and cooperation. But we also inherit the subtle, enduring marks of its creation. Studying this impact does more than satisfy historical curiosity. It offers a profound lesson in ancient resource management. It shows us societies capable of marshalling and consuming materials on an almost industrial scale. Long before the industrial age, they understood their environment intimately, leveraging its gifts and at times taxing its limits. This connection forms a quiet bridge between their world and ours. In an age increasingly concerned with sustainability and our own footprint on the planet, these ancient endeavors stand as both inspiration and caution. They remind us that our greatest works are always in dialogue with the earth, and that the true cost of moving mountains is written not only in stone, but in the very land from which they came. The rhythm of a drumbeat could move a mountain. That iconic image of hundreds of laborers straining on ropes is more than a symbol of collective effort. It is a precise engineering system. The true power of the human chain did not come from muscle alone, but from perfect synchronization. A disorganized pull is a lesson in wasted energy. If one team heaves while another rests, or if tension comes in staggered waves, the forces work against each other. The colossal stone would shudder and stall, its immense weight fighting the very people trying to move it. To overcome this, ancient overseers turned coordination into a science. They became conductors of human force. Using drums, rhythmic chants, or blasts from horns, they established a cadence that every worker could feel and follow. The call would ring out, a collective breath would be held, and then, on the downbeat, every back would bend, every rope would tighten as one. In that moment of perfect unity, the crowd ceased to be a crowd. It transformed into a single, living machine, a biological engine where the sum was far greater than its parts. This was applied biomechanics on a grand scale. The rhythm did more than coordinate. It actually made the work more efficient, allowing for periods of tension and brief recovery, a sustainable pace that could be maintained for hours across great distances. The training and discipline required were immense. It was not just about strength, but about listening, about trusting the person next to you, and subsuming individual effort into a collective pulse. This method fundamentally rewrites the equation of what is possible. A single person can pull with a force of, perhaps, 50 pounds, but 1,000 people pulling in perfect unison are not merely adding their force, they are multiplying its effect by eliminating internal resistance. The physical limit of human strength dissolves when that strength is perfectly aligned. The stone no longer faces a disorderly crowd. It faces a single, irresistible will made manifest through rhythm and trust. The journey of the monolith, then, was also a journey of the community, every step forward a testament to their ability to act as one entity. This invisible architecture of cooperation may have been the most sophisticated tool on the worksite, proving that the true foundation of these ancient wonders was not just in the ground, but in the synchronized heartbeats of the people who built them. The most persistent myth about these ancient wonders is also the most dismissive. For decades, a popular narrative has suggested that the construction of the pyramids, the movement of the Moai, and the precision of Stonehenge were simply too advanced for the people of the time. This idea that extraterrestrial beings must have intervened with otherworldly technology makes for thrilling science fiction, but it fundamentally fails as history. More importantly, it commits a profound injustice, stripping ancient human cultures of their greatest legacy, their ingenuity. Every single method we have explored, from the lubricated sledge to the walking statue, operates on principles of physics we can observe and test today. They required no anti-gravity devices or laser tools, only a deep understanding of leverage, friction, and teamwork, combined with materials readily available in their environment: wood, rope, stone, water, and earth. To claim otherwise is to impose a modern bias, a subtle arrogance that assumes our ancestors were incapable of such brilliance without outside help. It overlooks the vast, coordinated social engines they built, the generations of knowledge passed down through trial and error, and the sheer, determined will that turns an impossible dream into a permanent monument. The real mystery is not whether aliens visited Earth, but how human beings, with nothing but their minds and their hands, learned to converse with the landscape and persuade stone to defy its own weight. That story of human perseverance, intelligence, and collaboration is not just plausible, it is documented in the very marks left on quarry walls and the worn paths leading to sacred sites. It is a story far more complex, more ingenious, and ultimately more inspiring than any fictional intervention. It reminds us that the capacity for greatness is not bestowed from the stars, but cultivated right here, in the enduring spirit of human curiosity and collective effort. The sea itself became a road for mountains of stone, for cultures whose lives were intertwined with coastlines, rivers, and lakes. The most logical path for a megalith was not over the land, but across the water. This 13th method, the use of boats and rafts, represents a brilliant fusion of maritime skill and monumental ambition. It leverages a fundamental principle, the buoyant support of water. A stone that would crush any wagon or require 1,000 laborers to drag could become almost weightless when cradled by a well-built vessel. The challenge shifted dramatically, from battling friction and gravity to mastering the arts of shipbuilding, navigation, and dock design. Imagine a massive, specially constructed raft, perhaps made from dozens of lashed-together logs for both strength and flexibility. To prevent the unstable, top-heavy load from capsizing in open water, builders likely added outriggers, secondary floats attached to the sides, creating a stable platform that could weather gentle waves and currents. The stone itself might have been loaded at a quarry side dock during high tide, floated onto the waiting raft as the water receded, and then secured with ropes. Once afloat, the real work was not pulling but piloting. A team of oarsmen or a single sail could then move this incredible cargo dozens, even hundreds, of miles along a coastline or across a sheltered lake with an efficiency impossible on land. This method shines a clear light on sites like Stonehenge, where the Bluestone's journey from Wales might have involved a coastal voyage. It also recontextualizes the transport of the Egyptian pyramid stones, where canals from the Nile acted as liquid highways directly to the plateau. The true ingenuity, however, lay at the journey's ends. Loading and unloading such a precious, heavy cargo demanded its own engineering. Builders might have constructed simple stone piers or wooden wharves that allowed rafts to be floated directly alongside. They could have used the natural rhythm of the tides, loading a stone onto a beached raft at low tide and waiting for the rising water to lift the entire assembly free. Or they may have built ramps that descended into the water, allowing a sledge to be pulled directly from the shore onto the deck of a waiting barge, and then reversed at the destination. This transforms our understanding of these projects. It shows that the builders were not just land-based engineers, they were also naval architects. Their toolkit included knowledge of hydrodynamics, seasonal currents, and tidal patterns. Moving a mountain by sea required the same careful planning as any ocean voyage, charting a course that considered weather, depth, and safe harbors. This connection between seafaring and stone moving reveals a holistic worldview. A culture's mastery of the sea for trade and exploration was directly applied to its most sacred terrestrial projects. The same hands that built vessels to cross oceans also built vessels to carry the foundations of temples. The water was not a barrier separating the quarry from the sacred site. It was the most direct and graceful bridge between them. It allowed societies to extend their reach, to gather special stones from distant, spiritually significant locations and bring them home by harnessing the oldest, most powerful road on Earth. Before a stone could cross a desert or climb a mountain, it first had to be convinced to leave home. The quarry was the birthplace of the monument, a site of violent, careful creation where solid bedrock was persuaded to become a movable object. This initial separation was a feat of engineering as critical as any transport method, demanding an intimate knowledge of the stone's hidden weaknesses. Builders became geologists, reading the rock like a map. They searched for natural fracture lines, bedding planes where the stone had formed in layers over eons. By inserting wooden wedges into these seams and then soaking them with water, they harnessed a quiet, relentless force. The wood would swell, creating immense, even pressure along the hidden fault. With a series of sharp cracks that echoed through the quarry, the rock would surrender, cleaving along a near-perfect plane. In other places, they used fire. By building a controlled blaze against the rock face and then dousing it with cold water, they exploited thermal shock. The rapid contraction caused the surface layer to shatter and flake away, weakening the stone so it could be worked free with stone or copper tools. For the hardest stones like granite, they might employ a patient, percussive technique, drilling a line of holes with a solid copper drill and abrasive sand, then driving dry wooden pegs into those holes. When water was added, the swelling pegs acted like a row of tiny, coordinated jacks, prying the block loose from its eternal bed. Each technique was a dialogue with the material, a way of asking the earth to release a piece of itself. But freedom from the bedrock was only the first step. Now this multi-ton block sat at the base of a sheer quarry wall. How do you move it from the pit to the path? The solution was often a masterpiece of micro-engineering. Workers might dig deep trenches around the block, creating a temporary island of stone. Then, using levers and ropes, they could tip it onto a bed of prepared logs or earthen berms, creating a starting platform. For quarries on hillsides, they constructed rudimentary ramps from rubble and soil, descending from the working face to the flat staging area below. Sometimes, they would even carve guiding grooves or slickways directly into the quarry floor, stone channels that turned the initial, precarious shuffle into a controlled, guided slide. The quarry was far more than a hole in the ground. It was a factory, a loading dock, and a training ground all in one. Here, the stone was given its basic shape, its weight calculated, and its first tentative movements tested. The challenges here were unique: a confined space, unstable slopes, and the constant risk of a block shifting unpredictably. Solving these problems required innovations that would later be scaled up for the epic journey. The methods perfected in the quarry, the use of levers for pivoting, the concept of a lubricated track, the teamwork needed for a synchronized lift, these were the foundational skills. Every worker who would later pull a rope across miles of desert first learned his craft in the dust and din of the quarry, understanding the personality and weight of the stone before it ever began its legendary trek. This initial node in the supply chain was where the impossible was first made plausible, where a piece of a mountain was carefully turned into a passenger, ready for its long walk into history. A steep slope was not always an obstacle to overcome. For ancient engineers, a hillside could be a gift, a natural accelerator for their monumental cargo. This is the principle of the gravity road, a method of controlled descent that turned a stone's own immense weight into its primary motive force. The challenge was not to move the stone, but to prevent it from moving too fast. Unchecked, a multi-ton block careening down a mountain would shatter itself and anything in its path. The genius lay in designing a system that could harness that wild potential energy and convert it into a slow, deliberate, and safe journey downward. Builders would first prepare the path, clearing boulders and leveling the worst irregularities to create a rough channel. Along this track, they might lay parallel rows of wooden rails or slick, wet clay to reduce friction just enough to allow movement, but not so much as to lose all control. Then came the braking mechanisms. Teams of workers would station themselves along the descent, holding fast to long, heavy ropes anchored to the stone or its sledge. These ropes were not for pulling but for holding back, As gravity began to draw the stone downward, the crews would apply tension, letting the ropes slip through their hands or around anchored posts in a controlled, measured release. It was a constant negotiation with momentum, a collective act of restraint. In other scenarios, they might attach drag logs or heavy timber skids behind the sledge. These would dig into the soil, acting as a natural brake that increased resistance the faster the stone tried to go. The process transformed the workforce from engines of propulsion into guardians of stability. Their role was to guide, to moderate, to translate a dangerous fall into a graceful, intentional slide. This method represents a profound philosophical shift in how these builders viewed their environment. A hill was no longer a barrier to be circumvented with ramps or a brutal incline to be conquered with levers. It was a resource. It offered a segment of the journey where the landscape itself would do the work, conserving the vital energy and morale of the people for the arduous flat stretches or the subsequent climbs that surely lay ahead. We can see the shadow of this logic in sites like the ancient quarries of Ollantaytambo in Peru, where enormous red granite blocks were brought down from a high mountainside across a river valley to the temple complex. A controlled descent would have been essential for navigating the steep quarry face. This approach reveals a sophisticated, almost intuitive grasp of physics concepts we now name potential and kinetic energy. They understood that a stone held aloft possessed stored energy, and that their task was to manage the conversion of that stored energy into motion, metering it out like water from a precious vessel rather than letting it burst free in a destructive flood. It was energy management on a colossal scale. The gravity road teaches us that ancient ingenuity was as much about intelligent restraint as it was about applied force. It was about listening to the whispers of the natural world and recognizing that the most powerful ally in moving a mountain was often the mountain itself. The same solution appearing in a desert, a jungle, and a mountain range presents a haunting question. Were these brilliant minds talking to each other, or were they all simply listening to the same silent teacher? This is the great debate between cultural diffusion and independent invention, a puzzle about how ideas move across a world without maps. When we see the lever used in Egypt, the counterweight in China, and the inclined ramp in Mesoamerica, we are witnessing a pattern that demands an explanation. On one hand, the ancient world was far more connected than we often assume. Trade routes were not just for silk and spices, they were highways for knowledge. An artisan traveling with a caravan from Mesopotamia to the Indus Valley might carry not only goods, but the memory of a technique he saw used to move a city gate. A captured engineer, taken far from his homeland after a conflict, might apply his understanding of friction to a new King's Temple project. Knowledge could diffuse slowly, organically, over centuries, adapting to new materials and landscapes as it traveled. This view paints a picture of a whispering network of human ingenuity, where a clever idea from one valley could, given enough time, echo in another continent. Yet there is a compelling argument on the other side. The principles of physics are not a secret to be discovered. They are a universal reality to be observed. A child playing with a stick and a rock discovers the lever. A farmer dragging a heavy log across mud discovers that wet clay is slicker. The fundamental challenges of moving immense weight, gravity, friction, stability, are the same everywhere. Faced with an identical problem, intelligent people separated by vast oceans could very well arrive at strikingly similar solutions. This is the concept of parallel invention, where necessity acts as a universal mother, birthing comparable innovations in complete isolation. The truth likely lies in the nuanced space between these two extremes. Some methods, particularly those tied to very specific cultural practices or complex ritual meanings, might have been unique developments. Others, especially the most fundamental mechanical principles, could have been both independently discovered and shared along trade routes, reinforcing and refining the idea as it passed from one culture to the next. This does not diminish their achievement, it deepens it. It suggests that whether through shared conversation or solitary observation, human beings possess a shared cognitive toolkit for solving problems. The lever in Egypt and the lever in Peru are not proof of contact, but proof of a common human logic. They reveal that when confronted with a stone that will not move, the human mind, in its brilliance, tends to ask the same kinds of questions and find the same elegant answers. This global tapestry of similar solutions, woven from threads of either communication or common sense, ultimately tells the same profound story. It is not a story of a single lost civilization or a gifted teacher wandering the globe. It is the story of humanity itself, repeatedly and independently reaching for the stars by first learning how to make the earth obey. The rope and the lever were not the only tools that moved these stones. A more powerful, invisible force was also at work, the shared belief that the journey itself held transformative power. In many societies, the act of moving a megalith was far more than a construction task. It was a sacred theater, a collective ritual designed to forge identity and demonstrate strength. This 15th method, the ritualized feat of strength, reveals that the stone's weight was not just a physical obstacle to overcome, but a spiritual one to be mastered. The difficulty was not an unfortunate side effect, it was the entire purpose. Imagine a specific, notoriously heavy stone in a village, one that every generation knew by name. For a young person coming of age, the challenge was clear: to move that stone a certain distance or to lift it just once. This was not a test of engineering, but of character. Using the same practical techniques of leverage and teamwork they had been taught, the individual or the group would confront the immovable object. Success was not merely about relocating a rock. It was about proving one's readiness to take on adult responsibilities, to contribute to the community's strength, and to literally embody the resilience required for survival. The stone became a silent teacher, and its movement was a graduation ceremony written in sweat and effort. This ritual dimension also served to legitimize leadership. In cultures across the Pacific, leaders were believed to possess mana, a spiritual authority and power. A powerful way to demonstrate this mana was to accomplish what seemed impossible for others, such as orchestrating the movement of a colossal stone or taking a central role in its journey. When a chief successfully directed such an endeavor, it was visible proof of his favored connection to the ancestors or the gods. It was leadership made manifest in physical terms, turning abstract authority into a spectacle of coordinated will. The community watching this feat did not see a simple logistics problem. They witnessed a living parable of their own collective power and the rightness of their social order. The groans of the timber, the chanted rhythms, the unified strain, all of this was a performance that reinforced their deepest values: endurance, cooperation, and shared purpose. The stone, in this context, was a co-star in the drama. Its immense weight guaranteed that the achievement would be memorable and worthy of stories for generations. It ensured that the rite was never easy, that it always demanded the absolute limit of human effort. This transforms our understanding of the entire process. The engineering was not separate from the ceremony, it was the ceremony's mechanism. The careful placement of a lever became a deliberate, symbolic act. The synchronized pull on the rope was a physical prayer of unity. The journey of the stone from quarry to sacred site was a pilgrimage for the entire community, with every hardship along the path imbuing the final monument with greater meaning. By the time the stone was set in its final place, it carried within it the story of that struggle, a permanent record of a people testing their limits and affirming who they were. The monument stood not just as an altar or a marker, but as a trophy from the greatest test the community could conceive, a testament written in granite that they were strong enough, together, to make the earth itself yield to their will. The path of a stone could also be a map of the heavens. Beyond the practical challenges of mud and slope, some researchers suggest these ancient roadways held a deeper alignment, charting a course not just across the land, but through the cosmos itself. Imagine a processional route stretching for miles from a quarry to a temple. To our modern eyes, it might seem like the most efficient or the only passable trail. But what if its direction was deliberately chosen to mirror the sun's journey on the longest day of the year, or to point directly at a sacred peak believed to be the home of a deity? In this view, the transport journey transforms into a walking ceremony, a terrestrial reenactment of a celestial event. Every pull of the rope, every inch gained, was not merely progress toward a building site. It was a step in a grand, slow-moving ritual that connected the community to the fundamental rhythms of their universe. The stone was no longer just cargo. It became a participant in a cosmic procession, tracing a sacred geometry laid down by the stars. This idea of aligned pathways does not lighten the physical load. Dragging an 80-ton block is brutally hard work, regardless of whether you are following the solstice sun or not. But it changes the meaning of the labor entirely. It provides a profound navigational and motivational framework. The destination was not just a point on a map, it was a point of spiritual convergence. The path itself became a teacher, reinforcing cultural knowledge with every mile. Elders could point along the route and explain how it mirrored the path of an ancestral hero or a specific constellation. The journey wove mythology into the very landscape, turning back-breaking logistics into a living story. We see echoes of this in sites around the world. The famous Inca road system, the Quhapacñan, did more than connect cities. It integrated the empire into a sacred landscape of mountains, orapus, and celestial observation points. While built for travel and trade, its routes often followed spiritually significant alignments. Similarly, the avenue at Stonehenge, the ancient processional approach to the stone circle, aligns with the midsummer sunrise. While the larger sarsen stones came from a different direction, the avenue's orientation suggests that the final approach for people, and perhaps for some stones, was choreographed to honor the solar cycle. This merging of engineering and cosmology represents perhaps the most sophisticated layer of these projects. It reveals a mindset that saw no separation between the practical and the sacred, between moving earth and honoring the sky. The builders were not just constructing a monument, they were aligning it and the path to build it with the invisible architecture of their beliefs. The true foundation of these wonders, then, may have been laid long before the first stone was cut, in the careful observation of the heavens and the deliberate, sacred plotting of a path from the mountain to the heavens. A glacier's slow retreat leaves more than polished bedrock in its wake. It leaves behind an idea, a fleeting opportunity born from the rhythm of thaw and freeze. In the far northern reaches, where summer sun turns winter's grip to rushing streams, ancient builders may have discovered a method as temporary as it was brilliant: the ice melt slipway. This concept turns a seasonal challenge into a seasonal advantage. Imagine a carefully prepared track, a shallow channel or smoothed groove carved into the earth, leading from a quarry on a high slope down to a building site in the valley below. Now wait for the peak of the melt. As the sun climbs high and the snowpack and glaciers release their stored water, workers would divert a portion of that flow directly into their prepared channel. The result is a temporary, glistening waterslide, a ribbon of liquid frictionlessness engineered for a single, precious purpose. A stone block secured on a simple sledge would be placed at the top. On the dry ground, it would be immovable, but on this thin, fast-moving film of meltwater, the physics change entirely. The water layer lifts the sledge's runners, creating a condition of hydrodynamic lubrication. The stone is no longer dragging, it is almost floating, hydroplaning on a cushion provided by the thawing mountain itself. The pull of gravity does the rest, drawing the massive load down the prepared path with a force and ease impossible in any other season. The beauty of this method is its profound alignment with natural cycles. It requires no complex machinery, only precise observation and timing. The builders were not fighting the environment, they were inserting their ambition into a narrow window of perfect conditions, a window that opened and closed with the sun's arc. This speculative idea forces us to reconsider the very calendar of these monumental projects. Perhaps the quarrying of stones was a summer activity when the rock was dry and workable. The shaping and finishing might have occupied the autumn, but the grand movement of the heaviest megaliths that could have been reserved for the short, intense weeks of the spring melt, when the land itself offered a slippery highway of its own making. It reframes these endeavors as exercises in deep patience and ecological harmony. The community did not necessarily labor year-round on transport. They waited for the world to offer its secret, for the ice to surrender its hidden energy and transform their landscape into a conduit for stone. This ephemeral slipway, if it existed, would leave almost no archaeological trace, vanishing with the last trickle of summer water. Its evidence is not in found tools, but in the compelling logic of the landscape itself. It represents the ultimate expression of a theme we have seen again and again, that ancient ingenuity was less about imposing a will upon the earth and more about learning its language, listening for the moment when the mountains themselves were ready to help carry the load. A stone's journey was underwritten by an entire economy. Before a single rope could be pulled, a society had to answer a fundamental question: who pays for the impossible? The sheer scale of resources required to move a mountain of stone reveals the political and economic heart of the civilization that attempted it. This was not a weekend project, it was a decades-long investment of a society's total surplus. The funding models varied dramatically, painting a portrait of how these ancient worlds were organized. In the centralized, god-king states like pharaonic Egypt, the economic engine was the state treasury itself, fueled by agricultural taxes, control of trade routes, and the vast personal estates of the ruler. The pharaoh was not just a political leader, he was the embodiment of the nation's wealth and divine will. His command could redirect the labor of thousands during the Nile's annual flood, when farming paused, turning seasonal unemployment into a monumental workforce. The grain silos that fed these workers, the copper for their tools, the linen for their ropes, all flowed from a complex, top-down administrative system that saw the pyramid not as a cost, but as an eternal investment in cosmic order and royal legacy. This was an economy of command, where the movement of stone was a direct expression of concentrated power, but not all megaliths were funded by god-kings. In more decentralized or egalitarian societies, the economic model had to be collective. Think of the early stone circles of Europe or the massive Moai platforms on Easter Island. Without a vast central treasury, these projects likely relied on communal contribution and social prestige. A village or clan might dedicate a season's surplus harvest to feed those working on the transport. Skilled artisans, the rope makers and lever crafters, might be supported by the community in exchange for their vital knowledge. In such systems, participation could be a social obligation, a way to gain honor, or a deeply held religious duty. The economic engine here was not taxation but shared purpose. The monument became a bank of social capital, its value measured in strengthened community bonds and demonstrated collective strength to neighboring groups. This was an economy of reputation and belief, where the stone's movement proved what the people could achieve together, not what a king could force them to do. The resources consumed were staggering, a hidden river of material flowing to the worksite. Beyond the obvious needs of food and water, consider the supply chains. The wood for countless sledges, rollers, and ramps required forest management or long-distance trade. The fibers for miles of heavy rope meant dedicated fields for flax or hemp, and specialists to process and weave them. Animal fats or precious water for lubrication had to be diverted from other uses. If draft animals were employed, their feed and care became another entire logistical branch. Each of these items represents a choice, a decision by someone in authority to allocate scarce resources away from immediate daily life and toward a distant generational goal. This allocation is a frozen record of that society's priorities. A state that can feed 20,000 workers for 20 years is demonstrating not just wealth, but an incredible administrative capacity to plan, store, and distribute on a colossal scale. It reveals a hierarchy of managers, scribes, and overseers, the invisible bureaucracy that made the physical miracle possible. Ultimately, the economic underpinnings expose the true nature of the labor. Was it coerced toil or voluntary service? The answer likely lies in a complex blend. Even in a hierarchical system like Egypt, work on a national project could confer status, a sense of participation in something divine, and provide secure rations in an uncertain world. In a communal society, the peer pressure to contribute could be immense, a different kind of social force. The movement of the stone, therefore, is more than an engineering puzzle. It is a ledger in the choice to invest a generation's surplus in a single, silent sentinel of rock. We see what that culture valued most: stability, glory, the favor of the gods, or the unbreakable unity of the people. The monument stands not only as a feat of strength, but as the final, solid expression of an ancient balance sheet, proof that a society's greatest construction is always, first, a construction of its economy. A straight path is a luxury ancient builders rarely enjoyed. The journey of a megalith was never a simple line from quarry to temple. It was a winding negotiation with the landscape, demanding a solution for every bend and turn. This brings us to a maneuver of elegant practicality, the pivot and roll. Imagine a colossal sledge laden with a 20-ton block of granite, gliding smoothly on its log rollers along a prepared track. Ahead, the path curves sharply around an outcrop of bedrock or the edge of a sacred grove. The question is immediate and critical. How do you turn something that weighs as much as 2 elephants without derailing the entire operation? The answer lies not in building a curved roadway, which would be a monumental task in itself, but in a clever, localized pivot. At the precise point of the turn, workers would position a large, immovable object, a hefty pivot stone set firmly in the ground or a massive timber driven deep into the earth. This anchor point became the center of a new, temporary universe for that single stone. As the sledge approached, teams would use their wooden levers to carefully lift its leading edge just enough to clear the rollers beneath it. With the front of the sledge suspended, they could then swing it laterally, pivoting it around that central stone like a giant door on a hinge. This was a moment of delicate balance and immense coordination. A single misjudged heave could send the entire load tipping dangerously. Once the front of the sledge was aligned with the new direction, the real finesse began. Workers behind the sledge would now have to reposition all the log rollers, sprinting them from the back of the now angled assembly and laying them out along the fresh path ahead. It was a logistical dance, a reset of the entire rolling track in mid-journey. This micro-solution within the macro problem reveals a breathtaking level of foresight. It shows that ancient planners did not just think in terms of distance and weight, they thought in terms of geometry and motion. They anticipated the need to change direction and had a standardized, repeatable procedure for it. This pivot point was not an improvisation, it was a planned feature of the route, perhaps even marked in advance by the surveyors who first scouted the path. The space required for this maneuver, a cleared turning circle, would have been factored into the route selection from the very beginning. This transforms our understanding of these ancient roads. They were not just cleared trails, they were engineered courses with built-in stations for complex maneuvers. The pivot and roll technique underscores a theme we have seen again and again: the ancient builder's genius for modular solutions. They broke down an impossibly complex journey into a series of discrete, solvable problems. Moving in a straight line was one problem, turning a corner was another separate problem, and it had its own elegant mechanical answer. This attention to the minutiae, the corners and the curves, tells us that their planning was holistic. They accounted for the entire reality of the terrain, not just the ideal version of it. The true monument was not just the stone that arrived, but the invisible intelligence that guided it around every single obstacle, ensuring that no bend in the road could ever be the end of the journey. These stones left their mark not only on the landscape but on the human imagination. Across every continent where these monoliths stand, you will find a shadow story, a myth. In Ireland, legends say the giant Fionn mac Cumhaill built the Giant's Causeway and flung massive stones across the sea. In the Andes, people speak of stones that moved to the sound of a sacred trumpet, guided by the will of the gods. On Easter Island, oral tradition tells of the Moai walking to their platforms, animated by the mana of a powerful chief. These are not just fanciful tales to entertain children. They are cultural memories, a profound and ancient form of data compression. When a society accomplishes something so monumental that it defies the everyday understanding of what is possible, the story of how it was done becomes too big for mere history. It evolves into myth. The giants, the gods, the magical chants, these are narrative codes for the sheer, overwhelming scale of the achievement. They are the human mind's way of grappling with a reality that felt, quite literally, superhuman. To say a god placed the stone is to acknowledge that the feat transcends ordinary human capability. To say a giant carried it is to give a face and a force to the collective power of thousands of coordinated workers. These stories preserve the awe, the mystery, and the profound respect the builders and their descendants felt for their own accomplishment. By listening to these myths, we gain a crucial insight that blueprints and physics experiments can never provide. We understand how the builders themselves likely perceived their work. This was not just engineering, not just labor. It was an act that touched the divine, a ceremony that bridged the world of people and the realm of the eternal. The rhythmic pull on the rope was a prayer. The rising ramp was a path to the heavens. The final placement of the capstone was a moment of cosmic alignment. The myth preserves the emotional and spiritual truth of the event long after the practical details of levers and lubricants have faded from common memory. This narrative layer is why these mysteries have captivated us for thousands of years. The stone itself is a question, and the myth is our species' first, most poetic attempt at an answer. It ensures that we never look at these silent giants and see only rock. We see a story waiting to be understood, an echo from the past that insists the impossible was once, miraculously, made real. Sometimes the earth itself refused to bear the weight. For builders facing a landscape of perpetual softness, a bog, a marsh, or the waterlogged fens of ancient England, the standard method simply would not work. A sledge would sink, log rollers would disappear into the muck. Here, the only solution was to build a road that the earth could not provide, a temporary highway that floated on the instability. This is the concept of the Corduroy Log Road, an ingenious and labor-intensive answer to the problem of impossible ground. The process was a study in modular construction. Workers would fell trees and trim them into sturdy logs of roughly equal size. Then, perpendicular to the intended path of travel, they would lay these logs side by side across the soggy ground, like the ribs of a great wooden ladder laid flat. This created a wide, firm track, a floating bridge of timber that distributed the immense weight of the sledge and its stone cargo across a broad surface area, preventing it from sinking into the soft earth below. The sledge, with its stone passenger, would then be pulled across this rigid, corduroy-like surface. The logs themselves acted as both roadbed and a fixed set of rollers, their rounded surfaces reducing friction for the sledge's runners. But the true cleverness lay in the road's recyclable nature. As the sledge reached the end of the laid section, teams of workers behind it would spring into action. They would retrieve the logs from the back of the track, the area already traversed, and sprint them to the front, laying them down again ahead of the advancing stone. It was a continuous, moving sidewalk, a renewable path conjured from the forest and laid down just moments before it was needed. This method represents a staggering investment in temporary infrastructure. It meant that before the stone could move an inch, an army of laborers had to first become road builders, harvesting and preparing enough timber to create a portable track that might stretch for hundreds of yards. The effort was immense, but it was targeted. It modified the landscape intensively, but only for the brief window of time required for the precious cargo to pass. Once the stone had moved on, the marsh would reclaim its silence, the logs pulled up and carried away, leaving barely a trace. This fleeting transformation of the land speaks to a profound determination. It reveals that for these builders, no terrain was truly impossible, only inconvenient. If the earth would not support their dream, they would simply bring a piece of the forest to support it for them. The Corduroy Road was not a permanent monument, but it was the essential, invisible scaffold that allowed permanence to be achieved elsewhere. It turns our understanding of these journeys inside out. The greatest wonders were not just moved across the landscape, they were sometimes moved across a landscape that was built, used, and dismantled solely for their passage, a ghost road existing only long enough to grant a mountain-safe passage through a swamp. The stone itself remembers its journey. Modern science has learned to listen, to read the faintest whispers left behind in the very grain of the rock. This is the field of wear analysis, where geologists and archaeologists become detectives, examining the microscopic signatures etched into ancient surfaces. It is a forensic approach that transforms theories into tangible evidence, turning every quarry road, every pathway, and every stone block into a silent witness that can testify to how it was moved. The process begins with a meticulous, up-close examination. Researchers use high-powered microscopes and three-dimensional scanning technology to map surfaces at a scale invisible to the naked eye. They are searching for distinctive patterns, the unique fingerprints left by different methods of transport. Imagine finding a series of long, parallel grooves cut into a limestone pathway leading from an Egyptian quarry. These are not random scratches. Their consistent spacing and depth match the exact width of a heavy wooden sledge runner. They tell a story of repetition, of a sledge loaded with immense weight being dragged along the same precise track over and over until it literally carved its own road into the bedrock. That is a fingerprint of the lubricated sledge method, written in stone. Other patterns reveal different stories. On the sides of a massive stone block, perhaps one destined for a pyramid's core, scientists might discover a distinctive polish, a smoothed area with subtle, curved striations. This pattern does not match the straight drag of a sledge. Instead, it aligns perfectly with the friction caused by thick, braided ropes. It suggests a point where teams used ropes to secure the stone, to lever it, or to control its descent down a ramp. The rope's fibers, under tremendous tension, would have acted like thousands of tiny abrasives, gradually wearing a signature into the hard surface. Even the bases of stones can speak volumes. A uniformly flattened and slightly concave underside might indicate it was carried on a cradle or a sledge for a very long distance, its weight constantly pressing and polishing against a wooden bed. Conversely, a base with isolated points of intense wear or chipping could hint at a more jarring, incremental method, like the pivot and roll technique used to navigate turns. This collaboration between geology and archaeology is crucial. The geologist can identify the mineral composition of the abrasives found in the wear marks, perhaps traces of quartz sand that was used deliberately as a grinding agent. The archaeologist can then match that finding to the local environment or known quarrying practices. Together, they cross-reference these microscopic clues with the broader archaeological context, the tools found nearby, the art depicting transport, and the layout of the ancient landscape. It is a process of building a chain of evidence. A single wear mark is a clue, but a constellation of matching marks across a site, all pointing to the same type of motion, becomes a compelling testimony. This scientific lens allows us to move beyond speculation about what might have worked and toward an understanding of what actually did. We are no longer just imagining the sledge gliding on wet sand. We are examining the very grooves it left behind. The stones are no longer silent puzzles, they are archives, and we are finally learning their language. The ocean's own breath could lift a mountain. For builders whose sacred sites hugged the very edge of the land, the relentless pulse of the tides presented not a barrier, but a powerful, predictable ally. This 19th method, the tidal advantage, reveals a genius for synchronization, where monumental labor was choreographed to the moon's silent clock. Imagine a coastal monument, perhaps a stone circle or a burial chamber, standing just yards from the high water mark. The quarries for its stones might be inland, but the final, daunting challenge is the last stretch, moving a colossal block from the beach to its permanent home. Here, brute force meets celestial timing. The process would begin with meticulous observation. Elders and planners would track the lunar cycles, knowing that the highest tides, the spring tides, arrive with the full and new moons. These windows of opportunity, recurring every fortnight, dictated the entire schedule. On a chosen day, as the tide receded to its lowest point, workers would spring into action on the newly exposed firm sand. They would maneuver a heavy stone onto a waiting wooden raft or a sturdy sledge, securing it firmly. Then they would wait. This pause was not inactivity, it was the heart of the method. As the moon's gravity pulled the ocean back toward the shore, the rising water would do the work. For a raft, the incoming tide would simply lift it free of the sand, floating the stone effortlessly, ready for oarsmen to guide it along the coast to a landing point nearer the site. For a sledge meant to be dragged up the beach, the tide's lift would break the static friction, that initial glue-like hold, making the first, hardest pull immeasurably easier. The water itself became a hydraulic jack, a natural lifting force available twice a day. This technique integrates multiple layers of knowledge. It is maritime engineering, requiring an understanding of buoyancy and raft construction. It is logistics, demanding precise timing so that hundreds of workers and their equipment are in place for a narrow, critical window. And it is astronomy, a practical application of observing the sky to harness the earth. The rhythm was everything. Work might halt for days waiting for the right tidal conditions, then erupt in a burst of coordinated activity when the water reached its peak. This tidal method paints a picture of ancient construction that feels less like constant, grinding toil and more like a series of orchestrated events, each time to a natural cue. It shows a society not fighting the sea but inviting it to participate. The movement of the stone became a partnership with the planet, a physical dialogue between human intention and lunar gravity. When that stone finally settled into its socket above the tide line, it carried with it more than the weight of the land. It carried the memory of the sea that helped bring it home, a permanent monument grounded in earth but born from the rhythm of the waves. Even the most brilliant plans could fracture under their own immense weight. Scattered across the ancient world, lying silent in forgotten quarries or along deserted pathways, are the broken dreams of the builders. These are the abandoned megaliths, the half-quarried blocks, and the shattered stones that never reached their destination. Far from being mere ruins, they are some of archaeology's most profound teachers. A colossal, partially carved statue still clinging to the bedrock of Rono Raraku on Easter Island tells a story of ambition interrupted. The deep, unfinished channels around its form reveal the exact quarrying technique. but its incomplete state whispers of a social or environmental shift that halted work forever. In the Aswan region of Egypt, the unfinished obelisk remains attached to the living rock, a monument to a single, catastrophic flaw. A fissure discovered deep within the granite during the final stages of work rendered the entire 1,200-ton project useless. That single crack in the stone freezes a moment of profound setback, showing that even the most skilled engineers were at the mercy of the material's hidden secrets. Along suspected transport routes, researchers sometimes find a massive stone that cracked in two during its journey, left where it fell. The fracture pattern is a data point, revealing whether the stone was dropped from a height, twisted under uneven pressure, or simply succumbed to a hidden internal fault. These silent failures map the points of maximum stress, the moments where the careful balance of leverage and control was lost. They show us the absolute limits of the technology and the materials. A broken sledge runner fossilized in mud or a groove worn too deep into a stone pathway tells us where friction won, where the physics of the day met an immovable threshold. These sites humanize the ancient endeavor in a way that a perfect pyramid never could. They prove that the builders were not infallible beings working with magical certainty. They were problem solvers facing immense, unpredictable challenges. Each failure forced a reassessment. Did they need a stronger type of rope, a different lubricant? A wider turning radius, the abandoned project was a harsh but necessary lesson, a pivot point that likely led to the refinement of methods used on the next attempt, on the next stone. This process of iterative learning, of trying, failing, and adapting, is the true engine of innovation. The ultimate successes we marvel at today were not first attempts. They were the final, polished results of a long and difficult conversation between human ingenuity and an unyielding physical world. Every finished monument, therefore, stands not just as a trophy of victory, but as a memorial to the resilience that refused to be defined by what was left behind on the path. A festival could move a stone faster than any army. The most powerful gatherings in the ancient world were not just for celebration, they were engines of coordinated action. This 20th method, the social leverage of festivals, reimagines the monumental labor not as a grim, year-long burden, but as a brilliant scheduling trick. Imagine a society that knew, with the certainty of the seasons, that at a specific time each year, its entire population would converge on a sacred site. This was not a random crowd, it was a pre-assembled workforce, united by faith and shared purpose. The logistical headache of gathering thousands of people from scattered villages simply vanished. They were already there, their hearts and minds already aligned by ritual. At the peak of the festival, when communal energy was at its highest, the call could go out. The sacred stone, perhaps already prepared and waiting nearby, needed its final journey to the temple. What might have been a wearying administrative task became a pinnacle event of the holy days. The pulling of the ropes transformed into a collective prayer, a physical manifestation of devotion. The social atmosphere was crucial. In the heightened spirit of a festival, participation was not a duty, it was an honor. The social pressure to contribute, to be seen adding one's strength to a sacred cause, would have been immense. To stand aside would be to separate oneself from the community at its most unified moment. This cultural calendar provided a predictable, renewable source of labor. A project that might take years of sporadic work could achieve critical leaps forward during these annual or biannual windows. The society did not need to support a permanent, dedicated transport crew. They could achieve the same result through intense, short bursts of synchronized effort, timed to the rhythm of their own beliefs. This method beautifully blurs the lines we insist on drawing today. There was no separation between work and worship, between the practical and the spiritual. Laying a road for the god stone was an act of piety. The sweat on your brow was an offering. the rhythmic chant that kept the teams in time was a hymn. The festival provided the soundtrack, the shared belief provided the fuel, and the stone, in turn, sanctified the gathering by becoming its focal point. We can see the shadow of this logic in traditions across the globe, from barn raisings in early American communities to the collective efforts seen in many cultures during harvest or New Year celebrations. It leverages the human desire for belonging and meaning, channeling it toward a tangible, lasting goal. The monument that resulted was more than a building, it was a memory made solid. For generations after, people could point to the great lintel stone and say, "My grandfather pulled the rope during the Feast of the Sun, and we all moved it together." The stone stood not just as an altar, but as a permanent testament to a day when the entire community became a single, living machine, powered not by coercion, but by a shared and joyous purpose. This realization invites a final, overarching reflection. After exploring 20 distinct methods, from sledges to social calendars, a unifying truth emerges. The silent earth has begun to speak. Our quest to understand how ancient builders moved mountains is no longer confined to what we can see on the surface. A quiet revolution is unfolding in archaeology, powered by technologies that act as extensions of our own senses, allowing us to peer through time and terrain. This is not about replacing the old theories, but about illuminating the hidden canvas upon which they were drawn. The most transformative of these tools is LiDAR, or light detection and ranging. Imagine a laser scanner mounted on a plane, firing millions of pulses of light through a dense jungle canopy. Where our eyes see only an impenetrable green blanket, LiDAR sees the ground. By measuring the time it takes for each pulse to bounce back, it constructs a breathtakingly precise three-dimensional map of the Earth's surface, digitally stripping away every leaf and vine. In the jungles of Central America, this technology has revealed entire ancient cities, vast agricultural grids, and most importantly for our story, extensive networks of raised causeways and roads. These are the very transport highways of the Maya, invisible for centuries, now laid bare as clear lines on a screen. They show us the planned routes, the gradients, the way the landscape was intentionally sculpted to facilitate the movement of people and materials. It is like discovering the blueprints after studying only the finished building. But what lies beneath the surface of those ancient roads? For that, we turn to ground-penetrating radar. This device sends radio waves into the earth and listens for the echoes as they bounce off buried features. It can detect differences in soil density, revealing the ghostly outlines of what lies below. On the Salisbury Plain around Stonehenge, ground-penetrating radar has mapped a complex ritual landscape of buried pits, post holes, and processional avenues that were completely unknown. It can identify the compacted soil of a long-vanished earthen ramp or the stone foundations of a forgotten loading dock. This tool lets us conduct non-invasive archaeology, to ask the ground a question and receive an answer without ever lifting a shovel, preserving the site while unlocking its secrets. From the sky and below our feet, we then rise to a vantage point just overhead. Drone photography, with its high-resolution cameras and ability to capture images at oblique angles, reveals alignments and patterns that are impossible to perceive from the ground. The subtle shadow of a buried ditch at dawn, the faint discoloration of crops growing over a stone pathway, the grand geometric relationship between a quarry, a road, and a temple complex, these vistas become clear. Drones allow us to see the landscape as an ancient planner might have, to appreciate the deliberate choreography of sacred geography. They help trace the likely path stones took by revealing the most logical corridors through a valley or the easiest passes over a ridge. Perhaps the most intimate new technology involves reading the Earth's biological memory. Scientists can now extract ancient DNA from sediment cores, a technique called sediment genomics. From a sample of soil taken along a suspected transport route, they can identify the genetic traces of plants that grew there thousands of years ago, or the microbes that thrived in disturbed ground. They might find evidence of non-native plant species, suggesting areas where humans repeatedly camped and inadvertently brought seeds. They could detect the DNA of domesticated animals like oxen, confirming their presence and role in the hauling process. This turns dirt into a historical document, recording which species were witnesses to the monumental effort. Together, these tools are granting us a new set of eyes. They allow us to see the ancient landscape not as a static backdrop, but as a dynamic, engineered workspace. We are moving from speculation about single methods to mapping entire logistical systems. The promise for the decades to come is profound. These technologies may finally allow us to trace a stone's journey from quarry to temple as a continuous, documented path. They might reveal entirely unknown methods, perhaps specialized way stations for rest and repair, or ceremonial plazas built specifically for the turning of a colossal statue. Every scan, every radar profile, every sediment sample is a whisper from the past growing clearer. The greatest chapters in the story of how mountains were moved may not be in the history books, but in the data we are only now learning to read. The most powerful tool for moving a mountain may have been a song. Across the ancient world, the arduous task of transporting a megalith was rarely a silent, mechanical process. It was often accompanied by a symphony of sound, rhythmic chanting, the beat of drums, the recitation of prayers. From an anthropological perspective, these ritual acts were far more than mere tradition or morale boosters. They represented a profound form of conceptual engineering, a method of weight reduction that operated not on the stone but on the human spirit. The belief was that through proper ceremony, through offerings and purification, the builders could appeal to spiritual forces, to ancestors or deities, to literally lighten the load. In their worldview, the stone was not an inert object. It was a being with its own presence, and its cooperation was essential. A chant was not just a work song, it was a negotiation. An offering poured onto the ground before the sledge was not just lubrication, it was a request for the earth itself to become more accommodating. While this did not change the physical mass measured in tons, it achieved something equally critical, a psychological weight reduction. The conviction that the gods were aiding the effort transformed the labor. A worker who believed he was pulling with divine assistance would approach the rope with a different mindset. The perceived effort could diminish, replaced by a sense of purpose that transcended muscle fatigue. Confidence would surge, not in their own strength alone, but in the certainty that they were part of a sanctioned, sacred endeavor. This collective belief forged an unbreakable group cohesion. When hundreds of people chant in unison, their breathing syncs, their movements align. They cease to be a crowd of individuals and become a single organism, a biological machine where doubt is silenced by the rhythm of shared faith. In this state, human performance is enhanced, pain is endured longer, coordination becomes instinctual. The impossible task begins to feel possible because the community has collectively agreed, through ritual, that it must be so. This method reminds us that technology never exists in a vacuum. It is always embedded within a cultural framework of meaning. For the ancient builders, the lever and the prayer were not separate categories, one practical and one superstitious. They were integrated tools in a holistic toolkit for achieving the impossible. The physical world of ropes and ramps and the spiritual world of chants and offerings were two sides of the same reality. To only analyze the sledge and ignore the song is to see only half the picture. It would be like studying a modern spacecraft by only looking at its metallurgy, while completely ignoring the mathematics and the software that guide it. The ritual was the operating system, the cultural software that allowed the hardware of wood and stone to function at its absolute peak. The true monument, then, was not just the stone that was moved, but the transformed state of the people who moved it. a state achieved through a shared story that turned back-breaking labor into a transcendent act of creation. This realization invites a final, humbling question. If belief could help move mountains in the past, what unseen forces might we be overlooking in our own greatest endeavors today? A single secret was never the answer. The true breakthrough of the ancient builders was not discovering one perfect method, but mastering the art of the combination. They were not searching for a magic key. Instead, they assembled a complete, adaptable toolkit, both physical and intellectual, and knew precisely when to reach for each tool. On the flat, compacted sands of a desert, the lubricated sledge and roller was the undisputed champion. But when that same sledge met a boulder-strewn field, the crews did not force it. They stopped, they switched tactics. Out came the wooden levers and the sturdy timber cradles. They would lift, pivot, and navigate the obstacle with a series of controlled, rocking motions before returning to the efficient glide of the sledge once the path cleared. This was not a failure of planning, it was the essence of it. The journey was a dynamic puzzle, and their genius lay in real-time adaptation. This integrated approach extended far beyond the mechanics of movement. It governed the very rhythm of the work. They synchronized their efforts with the world around them. In the north, the deep freeze of winter meant ice roads and gravity-assisted slides. In the spring, the rush of meltwater could become a temporary slipway. In agricultural societies, the off-season between harvest and planting opened a window where the entire community's labor could be directed toward the monument. They did not fight the cycles of nature or society. They wove their ambition into them, turning constraints into powerful, scheduled advantages. The organization behind this fluid operation was a masterpiece of social engineering. It required a structure with the precision of military logistics and the unifying spirit of a sacred festival. There were overseers who mapped the routes, engineers who calculated angles of ascent, and quartermasters who managed the endless supply chains of food, water, rope, and timber. Yet the fuel for this machine was often spiritual fervor. The belief that moving the stone was an act of devotion transformed exhausting labor into a shared, transcendent purpose. The rhythmic chant that kept pullers in sync was also a prayer. The offering poured before the sledge was both a lubricant and a request for divine aid. This fusion of the practical and the profound created an unstoppable social engine. So we must let go of the romantic notion of a singular, lost secret whispered from a master to an apprentice. The reality is far more impressive. The ancient builders succeeded through a holistic, systemic form of intelligence. They saw the challenge not as one monolithic problem, but as a sequence of interconnected puzzles, each demanding its own solution from their vast repertoire. They combined physics with faith, calendar with cargo, and individual strength with collective will. Their legacy, therefore, is not just the silent stone that stands at the end of the journey. It is the brilliant, flexible mindset that made the journey possible at all, a timeless lesson in looking at an impossible task and seeing not a wall, but a series of doors, each waiting for the right key. From the rocking statues of Easter Island to the water-slicked sledges of Giza, the story of moving mountains is ultimately a story about us. It is a testament to human creativity, cooperation, and an unyielding drive to leave a mark on the world that would echo across millennia. We have journeyed together through over 20 methods, from the solidly proven to the intriguingly speculative, and each one has revealed a new facet of ancient genius. These builders were master physicists without equations, logisticians without computers, and motivators who understood the human heart. They did not seek to conquer the world as they found it, but to work in concert with it, to listen to the whispers of sand, water, stone, and season. Their true legacy is not locked in the silent stones they left behind. It lives in the enduring question their work forces us to ask ourselves. If they could achieve so much with so little, with nothing but observation, ingenuity, and shared purpose, what are the true limits of our own potential today? What mountains, metaphorical or real, could we move if we applied that same holistic, patient, and collaborative spirit? We would love to hear which theory or method captured your imagination the most. Share your favorite in the comments below, and if you enjoyed this journey into the depths of human ingenuity, subscribe for more explorations into the mysteries of our past. Keep wondering and keep looking at the ancient world not as a place of lost secrets, but as a mirror reflecting the incredible things we are all capable of together.